Hi guys, it's your guy Olumide, and today we are gonna be solving another one of the most commonly asked tech interview question, which is the combined sorted linked list. So it's a DSA question that is commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. Let's go into it. The problem statement states that given k singly linked lists, each sorted in ascending order, combine them into one sorted linked list. So as we can see in this example that's given, we have three singly linked lists here. This is the first, this is the second, and this is the third, and we are asked to combine them. So they are sorted, but we want to combine them into a singly linked list now. And as we can see, intuitively we see that one will be here, then followed by one. We have to sort them in ascending order. So followed by one, followed by three, just like here, then four, then six, then six, then seven. So, and that's what make up this sorted linked list. Now, a good way to start solving this problem is to figure out how to merge two sorted linked lists. Fine, we are giving up to 3 and we can be given as much as possible, but first let's work on just two sorted linked lists. Let us consider these two linked lists here, node 1 to node 3 and node 2 to node 4. So to merge these two linked lists, we're gonna place the pointer we're gonna initialize the pointer at both head node of the two linked lists now. And what we're gonna do is that we're gonna compare the node at this pointer. This is node 1, this is node 2. Now node 1 is smaller than node 2, so we're gonna place this node 1 as the first node in our output linked list, which is going to combine the merge one. And what we're gonna do is that we're gonna advance this pointer to the next element or next node in the linked list for comparison again. So advancing it to the next node in the linked list, we're gonna compare it with the second pointer, or the node that the second pointer is pointing at. And at this point we see that node 2 is actually smaller than node 3. So now it's time to add node 2 to the output linked list. Then what we do again is that we're gonna advance this node 2 again to this to the next node, which is 4 right here. And advancing it, comparing now, we see that node 3, which is being pointed to by the first pointer, is less than node 4. So we have to put node 3 there right now. And then putting node 3 there, we then advance our right pointer, and then we can see that the right pointer have actually get to the end of the linked list. So everything that follow at the left pointer, at the pointer 2, will be added and merged to the linked list, which is just 4. So, and that's why we merge 4 to the linked list. So we see that this is a way whereby we can sort two, and we can sort and merge two sorted linked lists by placing and initializing two pointer and comparing the nodes at these pointers. But what if we have more than two linked lists? Combining two linked lists involve comparing two nodes at each iteration, just like we did. So combine k linked lists now, where k is the number of linked lists that we are trying to combine. Combine them will require k comparison at each iteration, which can be quite inefficient if the length of k is much. Probably we are dealing with 1,000k or 1,000,000k now. That is, at each single iteration we are gonna do k comparison, that is 1,000,000 comparison, which is not very efficient. The reason we need to make so many comparisons is that we don't know which node has the smallest value at each point or at any point in the iteration. So it requires us to search through all the possible nodes at that iteration or at that point. Now I think it will be more efficient if we could find a way to access the smallest node, or the node with the smallest value at each point. And we know that a minimum heap would be efficient in getting this. Why? Because a minimum heap knows how to sort and order the node and each element such that the minimum one, that is the node with the minimum value, will be at the top of the heap, and therefore we can have efficient access to the smallest value at any point in time, because even after having efficient access to the first smallest value, after removing it from the heap, it gets reordered such that the next smallest value will be at the top of the heap, therefore granting us efficient access at any point in time. So a minimum heap is going to work in solving this problem. So we can as well use the same approach that we talked about earlier, but instead of using pointers, we're going to be using a minimum heap. So let's look how a minimum heap is going to help us solve this problem involving 3 sorted linked lists right here. So first of all, we populate the heap with the head of all k linked lists. That is, the head node of all k linked lists will be populated in the heap, so that they are ready for comparison. And this is how it look. So don't forget, a linked list too can be a little bit tricky. It's actually not like a list that you have to define every contiguously 1,6 or 1, no. A linked list, you can just with the head node, it links to its next node, and it chains on like that. So all we just need to pass into the heap is the head node of all k linked lists. Now let's implement our idea, our strategy of popping the smallest node, or the node with the smallest value, to the output linked list. So we're gonna be using a dummy node to initialize our linked list, so we can have easy access to the first node, because we know that dummy.next will give us the first node in the linked list. So don't forget, we don't have access to the first node. We are just gonna select it right here from the heap. The heap actually have a way of placing the minimum node, or the node with the minimum value, at the top. So the heap is gonna sort that out, and all we have to do is just to pop out of the heap. So it's gonna get us the smallest, is a minimum heap, so it's gonna get us the smallest node, or node with the smallest value. So we're gonna add it to the output node. So, and then what we're gonna do is that anytime after we get the smallest node, we then try to check if that node, just like this particular node that we got now, because it's the smallest, well, there's another smallest, but at least is one of the smallest node. We're gonna check if it has a next node. So we're gonna push that next node into the heap. Well, we are popping out this particular node now. Once we have it out, we are gonna check if it has a next node and push that one into the node. The essence of doing this is that we actually want to sort every node. Don't forget that this, for each of these k linked lists now, they actually have a head node that links to a next node that links to a next node, and we need to sort each and every one of the node contained in each and every k linked list. So that's why we have to push it there, so that we can we can also sort it as well. So, and that's what we did there. We push it. After pushing it, don't forget, we are gonna add that particular node that we pop out into the output. So pushing it now, we are gonna check again for the smallest node. Don't forget that whenever we make a push or a pop, or both a push and a pop, if the heap data structure knows how to sort it such that the smallest node will be at the top of the heap. So whenever we do a pop again, this particular smallest node, which has a value of 1, will be popped out, and it will be added to the output. And if it popped out, we are gonna push the next node back to the heap, and it is right here. So considering this new heap now, it's gonna restructure itself, and then this node 3 is the smallest node, so it's gonna be at the top of the heap. And what we're gonna do is that we're gonna pop it out again, and popping it out, we're gonna add its next node into the heap, and this is it right here. So again, 4 is the smallest node, we're gonna pop it out. So that's how we keep doing. Popping 4 out, we're gonna add the node 6 into the heap, and now we see that 6 is the smallest node now, so we're gonna pop it out. So there's really nothing to add to the heap now, because it does not have a next attribute. So we are just gonna pop it out and add it to the output, and now we have just 2 nodes inside the heap, and this is still the smallest node. So we're gonna pop it out again, and popping it out, we should have one thing right here, so let me quickly fix that now. So we are gonna have a node 6 right here again, and after that we have the last node in the heap, so we're gonna pop it out and we're gonna have a similar node 6 right here. So let me quickly sort it. So okay, so right here, and we have it. You see that this is a very efficient way to solve this problem using the heap data structure without having to perform k comparison. So once the heap becomes empty, we can return dummy.next, because we know dummy.next is going to be referencing the first head of this new merge sorted linked list. So return dummy.next is going to return this whole linked list to us now, and we have the sorted linked list. So that's how simply we can solve this problem using the heap data structure. Now let's move into the code implementation. Now let's go into the code implementation for the combined sorted linked list. First, we're going to be defining a class list node that's going to help us initialize the nodes, just like you can see in the slide below. So we have nodes in our linked list, and this node will be represented by the class list node. So we have self, and so we'll be passing a value into it, and now we have self dot value. Don't forget that node have two things, that is nodes have basically two things, value and then the next attribute. So we are gonna set the next attribute to none by default. So yeah, and now let's start defining that structure that you can see on the screen. And here it is. We define the first node, node 1. Then we define we have three linked lists. Actually we have three linked lists. One that node 1 that connects to node 6, then we also have the one of node 1 that connects to node 4, then to node 6, and we have node 3 that connects to node 7. So what we're doing right here is that we have two node 1. So, and actually it is not the same. That they have the same value does not mean they are the same node. So we have to create the two instances separately. That's why I call this one node 1 underscore 1, and I call this one just node 1. So similarly, you will be seeing node 6 and node 6 underscore 1, because node 6 we have two nodes that have the value 6. So we have to create these two nodes separately. So I'm calling them node 6 and node 6 1. So similarly, we have node 4. So I first of all created every node, and then I start to connect them to each other right here. So I connect the next attribute of node 1 to node 6. Then I connect the that's done for the first linked list 1 to 6. So the second linked list 1 to 4 to 6 is what I did here. Node 1 underscore 1 dot next, I connected it to node 4. Then node 4 dot next, I connected it to node 6 underscore 1. So that's it. So this is the third linked list that connects node 3 to node 7. So I've created the structure now in terms of code. I mean, we have created the code implementation of that structure, that three linked list structure. And now we have this. I define a variable that contain a list of these three linked lists: the first node 1, the second node 1 underscore 1, and then the third node 3. So don't forget, the problem is to sort these three linked lists. So I'm passing it as a list now, and then I'm calling I'm printing I call this function print linked list. So we're gonna be defining it here in the code implementation. So actually the function is combined sorted linked list, so that's gonna sort it and return the sorted linked list to us. But this print linked list is gonna give us a visual representation. Don't forget that the linked list is actually a class, so Python is not gonna give it to us in a visually appealing way. So I have to create another helper function that will convert it into something that can be more interesting to see. So let's go into the code implementation right here and start. Let's first of all define the combined linked list function. Def combined linked list. So it's gonna be collecting a linked lists. So So it's a list of linked list. So it's a list of list node. So because it actually contains list of list node, and then the return will be a list node. Don't forget, it will be the sorted. So sorted linked list, so which is a list node. Why? Because after sorting the linked list, we just have to return the head node. So the head node is going to connect us to the rest of the nodes. So now let's create a dummy linked list that will make us to be able to access the head node. So we're going to create a dummy, just a dummy, you understand? So just there to represent the head temporarily. And let's create this reference to dummy. So you will see very soon why we need to create the reference. So this one is just a reference to dummy actually, and you're gonna get it soon. So while linked, so first of all, before we apply while, let's import the function, ipq function, that's gonna help us to convert our linked list. So it's a list of nodes, right? Head nodes. So we're gonna convert it to an heap. Don't forget, from the visualization, from the logic I explained, we have a heap that contain a linked list, and then so alright, now we are gonna use ipq.heapify, so to convert the linked lists into an heap. So it's gonna do this in on times. So on time, where n represent the length of the or OK time, so where it represents the length of the head node that we pass, in this case 3. So what we do now is that we have converted it to a linked list, and so an heap. We've converted our linked list to an heap, so it's gonna get it sorted in the right way. So now to have an access to be able to customize how the nodes are sorted, I mean how each linked list are sorted inside this heap that we are right now, we are going to define the less than this less than custom function. So and we are going to pass in order. So when we this function I forgot the name they call it really in Python. So you don't have to call the function, it's gonna allow you to be able to use operators like less than operator, greater than operator, without having to call the function itself. So and what we're gonna do is that we pass in order, because we are gonna be comparing this particular an instance of list node with another instance of list node. That's why the other instance is what I call order. So right now we want to a less than, greater than, we always return either true or false, right? So we want to return self dot value is less than or equals to order dot value. So and what this means is that if the value of a particular node is less than or equals to the value of another node, then this particular function should return true. And what we are doing it here is that, don't forget, we are not just passing a number. This linked list is actually not a list of number, right? If it's a list of number, you don't have to pass to create any function, because number is easy to compare. But these are linked lists. They are actually class objects of the class list node. So we need to create a way whereby the heap method is going to be able to compare a linked list or a node with another node, right? That's why I have to create this function here. So with this function now, we can easily navigate and pop out, push and pop and do all those operations, whereas the heap is going to be able to maintain the smallest node at the top of the heap as we go along. So it's gonna be maintaining it on the basis of what we defined there, that if the value of the current node is less than the value of the other node, then return true. So if it returns true, it will keep putting that particular node that is less than the other node at the top, and therefore we will be able to do what we want to do. So now let's continue. While linked list, don't forget this our linked list has been converted into an heap now. So we can just pop out of the heap, because the linked list is now a heap. Heap dot heap pop. Why we are doing heap pop is because we are guaranteed that, because the linked list is actually is actually a heap, we're guaranteed that whenever we perform a pop, it's gonna get us the very smallest node in the linked list in the heap, which is still the same as linked list because we've actually converted it in place here, right? So getting that node now, we want to set our current.next. So this is where we'll be needing current. Now don't forget, current is a reference to dummy, so it's just like saying dummy.next now equals to node, right? And then we now say our current equals to current.next. Why we do this is because we are trying to create a long chain. We are trying to merge. So after setting current.next here, which our current is initially dummy, after setting its next attribute to node, that means that dummy now, the dummy node now have a node, is now connected to a node. We now need to set this current. This current is actually a variable. You understand? We now need to change that variable to reference current.next, which is the next, which is this particular node that we set to the next attribute of dummy. So that way now it is that node that is the current node. So if we're going to attach another node, we're going to attach it to that node. So that's what this actually means. So that way we are going to be forming a long chain. So after doing this, popping out the smallest, that's what we want. We want to sort it in ascending order of the node value. After popping it out, what we want to do again is that we want to now check that if node.next, right, that is if this node that we pop out have a next attribute, then we want to push it into the heap q.heap push heap. We have to call the where we want to push it into, so which is our linked list, comma, and what we want to push into the linked list now, so it will be node.next. So don't forget, from the logic we need to perform this so that it can reach every node in every of the k linked list, each of the linked list that you pass. So after doing this now, right, we can just return dummy.next. So meaning that it will keep running this function until there is no node in the linked list any longer. So, and at that point, every node that have been removed from the linked list is guaranteed to be sorted in dummy.next now. So, and we just return dummy.next. So, but this dummy.next is actually referencing a list node, right? And a list node is actually a class. So if you print a class, have you ever tried printing a class object or instance of a class? It will just give you some main object, something that actually that might not be understandable. So what we want to do now is I want to create a helper function, therefore print linked list that will collect this dummy.next, that is the head node of the newly sorted merged linked list. So we want to print it in a very representable format. Print linked list of we're going to be passing in the head node, which we expect to be the dummy.next, is also a list node, and so we're going to be returning a string actually, so a more representable string. So let's define strings x as let's define something like this as empty. So it's the string we're going to be removing. So why head? What I want to do is I want to traverse the linked list, right? And want to traverse it, and at each point we want to say string s equals to string s plus, we keep concatenating string of head dot value. So that is for that particular head node, we extract the value attributes. So we will now format it in this way. So and then we can return strs. So it might look a little bit tricky, but all it's just doing is that, okay, fine, thank God, we now need to set our head to what? Head.next. So we are traversing the linked list, and at each point we are trying to concatenate to append that head value, the value of that head, I mean the node, the value of the node. We are trying to concatenate it into a string so that it can give us a more representable format, right? So now let's run the function and see what we're talking about, because we've defined the combined sorted linked list function. We also defined this particular one for more easy representation. So right now we have it printed right here, right? 1 1 3 4 6 6 7. So if we not use this helper function now, we will hardly be able to know and hardly be able to know that this is how this thing is printed as. But now with the help of the helper function, we can see exactly that it is sorted, because 1 1 3 4 6 6 7 signifies that the we now have a sorted matched linked list out of the 3 linked lists that we provided in the function. So alright, you see it's solved now. So if we don't use that helper function, well, the maximum or the best is just gonna give us is just 1, because it's just gonna return this head node alone. But we pass that head node to the function, and the function keep printing the next and concatenating it into a string that is understandable. So this is how you solve this problem, and I hope you understand it. So if you do, kindly like, comment, subscribe to my YouTube channel. Please subscribe, please. Thank you.